This equation should be familiar to you. It's the volumetric expansion of the universe. And something on here that I would like to point out is that the row here and the row here are row zeros, indicating that they are constant. Now, what I have discovered, and I will show that later, is that that row here is not always a constant. If you use a value for rho that is exponential, it will describe Newtonian gravity. It will describe why the stars go around spiral galaxies at the same velocity, and it will probably explain many more things as they pop up in the universe. As far as I'm concerned, I'm not fully aware of all the distributions of matter throughout the universe, but basically this row here is very important for describing local situations of the general expansion equation. Now, what good is this whole thing here? Well, that's what I'm going to show you right now, because what I did was I described the universe just using Hubble's law as a basis, and the fact that the expansion is at a maximum, meaning HOR 0 is equal to C0. Now that's the maximum because C0 is about 3 times 10 to the 8th meters per second. That's what we recognize as the speed of light. And what I am claiming here is that the standard model has a constant speed of light when actually it is C0 e to the h0 t. It is expanding with the universe, and that is equal to c. The reason why this can be done is because the universe is expanding with the same expansion factor, and consequently the measurements will be the measurement of the speed of light anywhere in the universe, regardless of your position, regardless of your velocity. The speed of light will be measured at 3 times 10 to the 8th meters per second by conventional methods. I don't know whether or not we could stand back and see what the universe looks like from some overhead view, but I'm sure it can be done mathematically. Now, what good is this thing? Well, what I did was that I said, well, why don't I see what a universe would look like if we just used Hubble's law as a basis for the entire universe. And remember, we're talking about a spherical universe where you have an observer in the middle at a position R0, which is, it's okay. And these things are all spreading out in different directions. When I say these things, we're talking about galaxies, and we're talking about proper galaxies. Now, this is a little review. Proper galaxies are ones that obey Hubble's law. Velocity of the particular galaxy is equal to some constant times the distance of the galaxy. And when you integrate both sides of this and spread it out, it comes out to be the equation R is equal to, for all of these galaxies, in the parade of galaxies are all moving outward from the observer, R is equal to R0 e to the h0 t. Now this t here makes R a function of t. It's an exponential function of t. As t increases, so does the distance from the observer. R0 is the same as Hubble's distance, That's R0. It's the radius of the universe. And we can write some relationships down that agree with Hubble. The speed of light times some t0 is equal to r0. Well, what is this saying? If we take the age of the universe and multiply it times the speed of light, we're finding out the radius of the universe. Now, why isn't this exponential, this expression? Well, the expression isn't exponential because if I put t0 down equal to r0 over c0, and we know that r over c, these are both e to the h0t, e to the h0t, and we're talking about the same time, so these two things cancel out. So this, by the way, this is t, capital T0. We know that this expression goes. What is this T0? Well, T0 is equal to 1 over h0, therefore Hubble's constant is 1 over T0. It has units of per second. Okay, per second are the units of Hubble's constant. Now, these things I've already discussed with you, but the whole idea is we may be able to figure out a mathematical way to describe all these motions. And the way we do it, I might also add one other thing here. H0 is equal to the inverse of the Hubble time. T0 is called the Hubble time. I don't have to write that. But there's one other expression that I brought up before, is that if you use this equation here, the H0 becomes the square root of GB rho 0 over 3. This differs from Schwarzschild's and Schwarzschild value and all the values, any other scientist that came out with HO. It differs from it because it differs by the square root of 2. And the reason why it differs, now remember, we're talking about the universe here. The reason why HO differs from their value, there's just 2 in here for them. It differs because all, believe it or not, general relativity is based upon Newtonian physics, Newton's law of gravitation. In one way or another, it always narrows down to that, and that's where this square root of 2 here is wrong, and that's what I'm stating in my model. Getting back to this is GE rho over 3. This is 3HO, you see, in this expression. It's because it's volumetric. Okay, and this, by the way, is an E to the GE rho, square root of GE rho T. Now I'm going to erase all this. This is the general equation for the expansion of the universe. And I'm doing the expansion of the universe because that's where I started out. And the universe is seen from an observer anywhere in the universe. And you'll see that the observation point, there's some question as to whether or not the Big Bang ever occurred. If you have a galaxy, its RA, galaxy A, is equal to a position of R0e to the H0t A. Okay, we're only talking about a single galaxy here, and our VA which is the radial velocity, V of R of A, V R A, is equal to H0 R0 e to the H0 TA. At this point in time, remember, these things are instantaneous. They change because we're changing all of that. That's what makes this hard to imagine, but it's easier to imagine than time dilation. But this is the velocity of this galaxy at TA. This is located TA away from some R0. Okay, so we have the velocity of this galaxy here. The position of this galaxy is here. Instantaneous velocities. As time goes on, we know the galaxy is going to be moving further away. Now, if I take a Maclaurin expansion, I believe that's how you spell it, Maclaurin. What he said was e to the little a, where a is much less than 1. It's a very small amount. Approximately equals a plus 1. Well, we know that these values here are very small. In a short period of time, a year, no, this can go up to T0. If that goes up to T0, then the Maclaurin expansion falls apart, of course, because T0 over T0 is 1, and that's not very small. It's not small compared to them. But in these expansions, a Maclaurin expansion of the first one says that HO, I'm sorry, let's just put it down like it is, RA. If I do an expansion of that, is approximately equal to, I take this and I go R0, this is H0 TA plus 1. Approximately, because that's an expansion of e to the HOTA. Well, if you do that, it means it's HOR0 TA plus, now the R0. And what that is the distance is equal to the original distance plus the speed of light times the time. Well, that's the new distance is equal to the original distance plus its velocity times time. It's the distance formula. If you do it for this, what should we get? We should get the new velocity is equal to the old velocity times the acceleration times the time. And do we get that? We get the V sub A is, well, this is C0. V sub A is HO R0, and then expand this, HO TA plus 1. And that's, if you look at this, it's H0 R0 plus H0 squared R, this is a 0 here, 0 T. This, if you remember, if we differentiate this, it becomes that. And therefore, this is the acceleration of that. And remember, we're doing a Maclaurin expansion, so we got rid of the e to the HOT. So this is new velocity is the old velocity plus acceleration times time. Those are the constant acceleration equations. So this seems to work, kinda. It does work, okay? Now what I'm going to do is draw some more realistic pictures and show you a galaxy that moves in a time delta t to this position. This is delta t. It goes from there to there in this amount of time, and we'll call this galaxy A, and this is its position RA, and this is position RA prime. It's the same galaxy, but it's moving in a period of time from A to A prime. Well, RA is R0 e to the H0 t A. It moves from there to R0 e to the H0 t A prime. Okay. Now, TA prime has a relationship to TA. TA plus delta t equals TA prime. And you could also say delta t is equal to TA prime minus TA. Okay? Very simple mathematics. Now if you look at this, you see that this could be written R0 e to the H0 TA plus delta t. Okay? So, what can we do with that? We can make a couple comments. First off, if you look at this, this is equal to R0 e to the H0 TA times e to the H0 delta t. This is an expansion factor here. What is this? This is RA. This is this. Okay. So you see that a new position of a galaxy is simply the original position times e to the H0 delta t. Okay? That goes to a new position, H0 delta t, where delta t is the change in time between the two positions. Now, if we take that and we go with, let's see, what else do we want to do? We want to specify that this is a proper galaxy, first off, that this occurs. We can't do this operation just like this with a galaxy that isn't going that far in delta t. This is a galaxy moving properly, and that means it's moving at HORO e to the HOT. It's moving at the speed of light. Okay. Now, this is RA prime. Now, what else can we find out? Well, what's the velocity of A? I may have done this already, but velocity of A is, differentiate this. Instantaneously, it's moving at that velocity. After delta t, what's its velocity? The velocity after delta t is velocity A prime. It's equal to H0 R0 e to the H0 T A prime. But this TA prime is TA plus delta t. So this is H0 R0 e to the H0. Why don't I just skip a step h0 ta times e to the h0 delta t. I'm sorry. Okay, so VA prime equals my original VA times e to the h0 delta t. Now what's that? That means that the velocity is increased by the same expansion factor that the position was increased. Okay, so if you want to know how fast the galaxy's moving from here to here, from this instantaneous velocity, what's this instantaneous velocity after delta t? This is what you would have. Just find out the expansion factor, e to the h delta t, and you just multiply it. Now, the displacement here is another issue, and what we want to do is find out how far has that gone? What's the distance between these two things? Well, from the distance, from common sense is you say I'm here, I was here, I subtract to find the distance between them, I subtract from this, I subtract this distance. Okay? Well, this is positional, so the distance I claim from A to A prime is equal to, okay, RA prime minus RA. Okay? Okay, so this is different than position. We're talking about how far is it between those two things here. And if you look at the units, that's what it says. I might also add here, by doing this kind of mathematics here, I will show you that light speed will be from a proper galaxy, or actually from any galaxy, is going to be measured at C0. The other thing that comes out of this kind of math is that if you have a universe like this, an exponentially expanding universe, the other thing is that the Doppler shift is just an the Doppler shift that we know on the surface of the Earth is just an approximation of a Doppler shift that is exponential. In other words, the Doppler shift that we use, the relativistic Doppler shift, is incorrect. And that's why the galaxies don't fall on the straight line of HO. And I will show you that too. There's a new Doppler expression. I don't know that you would call it a Doppler shift because it's not derived like that. But the reason why there is a redshift is not because of the Doppler equation or the relativistic Doppler equation. Now, the equation that I come out with will, of course, have to correspond to what we see on the Earth as far as Doppler shifts, and it does. It's got to correspond, and it does. But I wanted to do one more thing here. What's this distance? D from A to A prime. Well, it's this form, and we're going back to positional things. This R A prime. R A prime is RA e to the h0 delta t. That's the time interval between the two positions. Okay. Minus RA, and this is dA A prime, is equal to this. So it comes down to the distance between these two things, and it's the instantaneous distance too. Remember that. Any of these values here are instantaneous, so if you want to know what you want to take a measurement, you better do it very quickly. But it's that was a joke. You can't. Okay, so this is equal to RA E the H0 delta T minus 1. Okay. Okay, that's the distance between the two. Yeah, let's see what would happen. I'm just thinking this right now. What if I do a Maclaurin for that? Because this delta T is small. That's approximately equal to RA. Now remember, RA is R0 E to the HOTA times Maclaurin H0 delta T plus 1 minus 1. The minus 1, this is plus 1. So these cancel out, and this becomes RA HO, that's C0. Yeah, that's CA minus delta T. So it's speed of light times the time interval. It's an approximation. Speed of light times the time interval. Our speed of light, we would be measuring from here. How long does it take to get to that galaxy? That's what they do now. It's an approximation. How long does it take to get to that galaxy? It's H0 hour speed of light times delta T, but you see in the exponential universe, it wouldn't be that. It's not that. It's this. The distance is that. So therefore, I'm going to now say, okay, this is all very nice, one position to the next position, but what about the distance between two galaxies that don't have the same factors? The one galaxy, okay, you find the distance between galaxies now, and will it be in a little while, and I'll show you that because there's an important consequence of that I will show you. Okay, so I'm going to put two galaxies up here, and that should be quite enough to understand what's going on. Galaxy, let's do it A again. We got an A galaxy and a B galaxy. I've drawn spiral galaxies here, fully aware that galaxies are full of stars, millions and billions of stars, and they all aren't spiral galaxies. There's elliptical, there are barred spirals, etc. But the proper galaxies A and B are represented here. Now, we've got some things we can find out. How far are these two things apart? In other words, what's the distance? Well, intuitively, we know that the distance between A and B is an instantaneous distance. We know that an exponential universe, everything's moving, and the distance at this time is going to be a greater distance later. These are instantaneous values. Well, let's look at this. What's the distance between here and here? Well, it's sort of like if somebody's in this location, the other person's at that location, you subtract the distance from you of each one. It comes down to B. This is RB. This is RA. Okay? And RA is equal to R0 E to the HOT, but let's just leave it RA. This is R0 E to the HOTB. Okay? That's what makes the difference between where these places are. These are positional. But a position is different than the distance between these, which we're going to represent as DAB. And we're going to say that DAB, the distance between these things, is simply RB minus RA. Okay? So if this is 10 meters from you, this is 3 meters from you, the distance is going to be 10 minus 3 is 7. Okay, here's the formula for it, but how do we do that? Well, we do what we did before. We say RB is equal to R0 e to the HOTB minus R0 e to the HOTA. Okay, that's the distance. Well, what's HOTB here? HOTB is as if this galaxy were to move to here. How long does that take? I'm going to make it a capital T. If this galaxy, forget this one, this is a position here. How long does it take this galaxy to go there? From there to there. Then we can rewrite this as RB is equal to RA times, good tool, e to the H0 delta T, capital T. Do you see that this is just saying at this instant in time, it will take delta T for A galaxy to go to where B is there. Okay? So you've got this, you've got this. This is RA. So, DAB is the subtraction of those two. RA, I'm gonna say RA e to the H0 delta T minus RA. RB minus RA is this is RB minus that. Now I could write the whole deal out, it won't make any difference. This is RA, this is RB. The general idea is that this is equal to that is a distance. Okay? This delta T represents how long does it take galaxy A to go to the position of galaxy B. Because we know very well if it takes some time to go there, delta T, during that delta T, B is moving on. A is never going to catch it. B is moving on to some other location. Okay? So that defines the distance between these two things. Now let me go a step further. Here's A. I'm going to draw these B, galaxy B. Let's go now. During a delta T, and I'm going to make this delta T little t, A is going from here to here. During the same delta T, B is going from here to here. Okay? What I'm saying is the original distance is delta T between these two things. That's capital T. The distance, we pick a time and say, okay, 5 seconds later, where's A going to be, where's B going to be at the same time? Okay, so this is A prime, and this is B prime, where A prime, or A prime, that's the location, RA prime, is equal to RA times E to the H0 delta T, little delta T. Now don't get that mixed up. This little d delta t is a time we picked, you know, it's going to go some, if these are many light years away in this 1 hour, it's going to be short of that location. Knowing that delta t is a bigger number. Now, it can be smaller too if you want. You could have them go to a position out here. But the idea is that we are taking the original position of RA and moving of A, we're moving it to A prime. And at the same time, what happens with B and B prime? And what we'll say is that our B prime is equal to RB times e to the same HO delta t, little t. Okay? Now, what has happened here? We have the original distance, DAB. This is the original distance between these two things. Okay? Now let's look at what happens to that distance, a distance. Okay, let me see here a second. This is A and B. This is AB. What happens to that distance? Well, it has the appearance that it's going to be bigger, right? But let's do the math. The math is subtract from this, subtract this. So we're finding. Let me find some room here. dA prime B prime. I hope I did that so it doesn't confuse anybody. But basically, I'm finding the distance from here to here. Now, how do you do that? D A prime B prime is equal to. This is the distance after delta t, little delta t. dA prime B prime, this distance here, as opposed to this distance here. dA prime B prime is equal to RB e to the H0 delta t. That's, I should have put R prime B, RB prime minus RA prime, but it's equal to RA e to the H0 delta t, and that's equal to R prime, RB prime minus RA prime. I should have put that first here to find that distance. This is the distance between them, but you see that we're in terms of RA and RB, and we know that RA is RA is, let's see, oh, RA is here, RB is here, so RB, let me write that some, RB equals RA, did this on the, oh, here it is, RA e to the H delta t, but that's the big delta t. Now I'm writing that down there. It should have been up here. Should realize that. RB is that. Okay? So what I have here is an expression with RB in it, but RB is this expression. Okay? So RB, the distance between A prime and B prime is equal to now RA e to the H0 delta capital T. Okay, that's just this times e to the H0 delta T little t. Okay, that's this minus this RA e to to the h0 delta little t. Okay, now let me clean this up a little bit. RA delta t, this is equal to RA capital, e to the h0 little t delta t. Taking that out of both sides. What is this? This is an E, yeah, okay. And I'm multiplying that by e to the capital HO capital delta t minus 1. Okay, we look at this and we find out that RA times this is this. So that's this times this is DAB. Okay. 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 Now, DAB is that, so therefore I'm going to change this. DA prime B prime is DAB. That's this times that times e to the h0 delta t, little delta t. So what does this mean? This means, this is important, it's a tool. After time goes on, delta t, the distance is increased by a factor of each e to the h0 delta t, expansion. So both of these are expanding by e to the h delta t. So therefore, if I have something like, say, a light wave that's a length, after time, the wavelength will increase. And we will see that the increase is determined by e to the HO delta t, and it presents a good argument against the methods that are used today to determine shift, Doppler shift. The relativistic Doppler shift in this model here is going to replace the Doppler shift. Unfortunately, I'm telling astronomers that it's what they've been doing for many, many years is incorrect. This is why the shift occurs, and it corresponds to what we experience on Earth. We have seen the two proper galaxies, one here and say a second one here. This is at a distance RA from some R0. This is at a distance RB. When RA displaces during a period of delta t, and that's a little delta t, RB goes to some new location, galaxy B. This is galaxy A, and this would be RA prime, RB prime, and it's the same delta t. Now, getting some things straight first is that the distance between these two, I should say the time interval between these two, let's call it delta T1, and that's a capital T. That is the time interval between there and there. It's the time it would take this galaxy to go to there. So we will call that the light time interval between the two. There is another possibility. I want to see what happens to the time interval between RA prime and RB prime, and let's call this delta T2. Now intuitively, since they're further apart now after some delta little t, we would expect that delta T2 is larger, and how much larger is it? This is the flow. These things are all moving in any direction in the universe because the expansion is in all directions. So what we want to find out is how is the time interval between galaxies, how does it change over time? Where the time interval between the motion of the motion is different than the time interval between the two galaxies. Okay, so what we want to do is we want to say this. We just learned something that dA B dA prime B prime is equal to dA B times the expansion factor H0 delta T, and that's little delta t. We also know that the dAB, I'm going to put some things down here that we've discussed already, is equal to RA, okay, times E to the H0 delta T1 minus 1. Now all I'm saying there is we found out how we're subtracting from RB, we're subtracting RA. And I could also call this RB minus RA. And we also know that RB is RAE to the H, RA times E to the H delta T capital 1. And this will give us a feel for an expansion where DAB gets larger as time goes on as it increases to dA prime B prime. But this is the formula for the distance between two galaxies initially. The initial one is there. Now what are we looking for? We're looking for dA prime B prime, where dA prime B prime is RA prime here to here times E to the H0 delta T, capital T, 2 minus 1. All I'm doing here is making the same statement about the distance between RA prime and RB prime that I made for RA and RB right here. Same statement. Let me change this. This is B prime. Okay, I don't think I have any other mistakes there. dA prime, B prime. Oh no, I did make a mistake. This is RA prime. Okay, consistent. DAB is equal to that. dA prime, B prime is equal to that. The delta T2, delta T1. We want to see what is the relationship between delta T2 and delta T1 in this example. Okay, how do we go about doing that? We look at some of the values here. What's RA prime? RA prime is equal to RA times the expansion factor H0 delta T little t. Okay? Now what that is, what this says is, you start with RA, and after delta T, it turns into RA prime. And in the same vein, RB prime is equal to RB prime, RB times E to the same expansion factor, delta T. Okay? So there we have two identities. This is consistent with what we've talked about before. And how we want to get to our eventual knowledge of these two things here, we will substitute things into here. We will say that dA prime B prime is equal to dAB, okay, times e to the h0 delta t. We just showed that in the previous board. dA prime B prime is equal to the original dAB times the expansion factor up here. In other words, this interval, time interval, passed. It went through a time interval of delta t. Both of these things did. This one went from here to here, here to here. This one went from here to here. Now we're looking at the new thing here, but this is true. We showed that in general, the original distance is equal to, your final distance is equal to your original distance times how long it was expanding. Okay? And we also have this right here is a statement as what dA prime B prime is, which is RA prime e to the h0 delta t2 minus 1. They both equal dA prime B prime. Okay? Now we go back here, we look, we're in terms of RA prime. I could put that in terms of RA. DAB, you see, can be put in terms of A or A. In other words, RA prime, if I look on here, is equal to RA times the expansion factor H0 delta little t. Okay, that's that. Okay, and then of course it's multiplied by e to the h0 delta capital T 2 minus 1. Okay, now on this side, DAB is equal to RA, and you can see that things are going to drop out. I'm going to go with this one. DAB is equal to RA times E to the H0 delta T, capital T1, capital T1 minus 1. Okay, and then it's times the expansion factor for delta little t. Okay, now let's look at this. I can cancel out RA. I can cancel out e to the h0 delta t. And I get e to the h0 delta capital T1 minus 1 equals e to the h0 capital delta capital T2 minus 1. These two are equal to each other. I'll let you figure that out, but what's it mean? Delta T1 equals delta T2. How could this be possible? Well, because this thing is increasing in velocity, even though RA prime or B prime is larger than it used to be, the velocity is greater, so the time it takes to go further is counterintuitive. The time it takes for the proper motion between these galaxies is constant. Delta T is constant. This is constant. Did I get that in? Okay, yes. This is a large, it's a pretty big thing. It's saying that the light time distance between proper galaxies is unchanging. And what are some of the consequences? First off, if you think of a universe with an R0 here, where R0 is C0, T0, if this T0 is constant, then the universe has the same light time radius. That's one way to look at it. The time it takes for light to get from the observer to the other side of the universe, to the edge of the universe, the visible universe, is constant. Another thing is that with size increases here, you got to realize as this thing, as the universe expands, everything's expanding at the same time, and what you see as an observer, you don't notice any you don't notice any movement. Even though the math says they're moving, they're really not moving. Not in the grand scheme of things. And what it also says is that this whole process is going to be continuous, and there was no Big Bang. This is like it is now and it was billions of years ago. So no Big Bang, and we will say, therefore, it is a steady state of continuous exponential expansion. This is a steady state situation, but it's not really like the steady state that Einstein and other earlier cosmologists were talking about. This universe is expanding continuously, yet remaining the same.